Bismillahirrahmanirrahim. So last time we started talking about the quality of service mechanisms, and I can say that starting from this chapter we're getting into the important stuff. So we started talking about the classification. We defined classification, and we talked about the different ways for or the different fields or entities that we can use in each layer to provide some identification based on which we can classify the flow or the user or the application. And based on that, we can provide special behavior for that user or application. So from the transport layer point of view, we talked about the five fields. We talked about the source port, destination port, and source address, destination address, and the IP protocol. These are the five fields. And we said that these five fields can uniquely identify the end-to-end connection. And of course, identifying the end-to-end connection has some limitation. We can provide some spatial behavior based on the end-to-end connection, usually at the edge network. And what that means is that if you have like a LAN, which is terminated by a router, okay, and of course you have here multiple workstations and users and devices and stuff like that. This edge router, they call it edge router, when it connects to the internet, of course the internet will have multiple large-scale routers, and then it goes to other LANs and stuff. So the limitation here talks about the fact that this edge router actually receives these five fields from a small number of devices. So it's doable that we can provide from that router point of view, we can provide special behavior for end-to-end connections at the edge level or at the LAN level or group of LANs. The problem is that this router receives millions of connections from the entire internet. So if this router deals with the 1,000 or 2,000 connections end-to-end, this router might actually deal with millions of connections. So to provide special behavior for end-to-end connection at the core router level is really not scalable, and it would be really hard from the complexity point of view. So it's not scalable. But at the edge router is possible because it deals with a few number of end-to-end connections. So this is the first limitation. The second limitation is, as we said, network address translation provides another limitation because it actually, if this router runs NAT, then the five fields that we talk about to identify the end-to-end connection will have to be altered, will have to be modified, right? Because NAT changes the source port and the destination port the source port and the source address to use the public IP to be able to talk to the internet. So if we do this, then we hide the identity of the end-to-end connection, right? So in that case, we cannot also provide special behavior for this end-to-end connection because the source address and the source port have been modified. Okay. So again, if you don't remember NAT, you need to go and refresh your memory about how network address translation really works. Okay. So these are the limitations when it to providing traffic behavior or different behaviors from the transport layer point of view. From the application layer, we have access to two things mainly. Either the application identification, so we can have some ID for the application itself that identifies that this application, for example, is FTP application, is a special application of some sort, or we can provide user identification. So for example, when a user logs in to the system, this user gets identified by a user ID and password. So this user credentials, they identify the user. So based on these credentials, we can provide spatial behavior based on this the user identity. So from the application point of view, we can identify the application, which we can sort of provide special behavior for, or we can provide the identification for the user. Based on that, we can allow or reject certain traffic that is coming from this application to go into the core network. Which is part of another mechanism that we'll talk about, which is admission control. So if this application is generating something and the ID of the application tells me that this application has certain priority, so I can allow this application or reject this application to come to the core network, or to allow but with certain boundary on the delay and which is the quality of service, the quantified quality of service parameters that we talked about. Okay. So mainly today we want to talk about channel access mechanisms, and this is not new. It should not be new to all of you. So channel access mechanisms is what we talked about in medium access control in 455. So channel access mechanisms, they talk about the fact that we have a shared channel, okay, and this shared channel could be like we are in a meeting like this, and we need to organize who will have access to saying something, okay, using certain mechanisms. So we can classify the channel access mechanisms into collision-based access, which means that we don't have initial control for who can talk when, okay? So we'll allow anyone to talk at any point in time, okay? But hopefully, we will not have disturbance. So we rely on the fact that if the number of people who want to say something is relatively low enough, we will not have disturbance from each other. So we can allow people to talk, but if two people are talking at the same time, the recipient may not be able to distinguish the talk from both sides, which is what we call for channel access mechanism, which is what we call a collision. So if two nodes are sending on the same channel, which is shared at the same time, this is collision, right? And at the same time, we mean at the same time at the same frequency, because as we will see in a minute, if we're sending on different frequency, it's fine. Even at the same time, but on two different frequencies, still it's fine. So we can classify the channel access mechanisms into collision-based access and collision-free access. So what's new here? So we talked about this before. We know medium access control. We know what's collision-based access is. We know what collision-free access is. We took some examples in 455 possibly, and if you had gone through network 2, as again we have discussed this in more details. Here, what we want to talk about is how can we provide service differentiation given specific channel access mechanism. Okay, so we need to control, but with some service differentiation, which means that we need to organize a meeting like this, but we need to distinguish certain people that whenever they want to talk, they should talk. If they are not talking, then others can share or can have like some best effort kind of service, that if they want to talk, we can allow them to talk, but there may be some disturbance from other people and things like this. But if certain people are trying to talk, like myself, like I have a special status here that whenever I want to talk, okay, so I can say whatever I want. So in that case, I have like precedence. I have some priority. So I have access by default to the channel whenever I say I want to say something. So for collision-based access and medium access control protocols, how can we guarantee quality of service? We can guarantee it because in medium access, in collision-based access, what is bad here? What is the cost here? What is the cost if there's collision? So this is the collision we're talking about. Okay, so what happens if there's collision?
Losing the data information.
Huh?
Losing the information.
Losing the information. Okay, so assuming that we have a reliable protocol, what will okay. So if there's collision, we lose the data, and if we want to recover this data, we have to retransmit, which means that the loss will be transformed into delay. In both cases, we have a problem, and this might be a problem for multimedia applications. Okay, so in undeterministic environment like this, if we want to guarantee quality of service, what will we do? Because we don't have control when the collision happens. Because again, we don't have control when people will talk. So if we allow people to talk in an uncontrolled manner, and we want to provide deterministic quality of service, then the most common way in that case is over-provisioning, which means that we will reject up to a certain level of number of users to talk or to share the channel. We will reject any other user who's trying to access the channel, which means that we will allow only few number of people with low expectation on the traffic rate to access the channel at the same time. In other words, we will try to reduce the collision because we cannot eliminate it. We will try to reduce the collision and make it as low as possible by restricting the number of users who are accessing the channel at the same time. Okay? Which means over-provisioning. Over-provisioning معناه because the traffic rate is variable from this number of users. So what we could do is to reduce the aggregate rate, so that we make sure that if the aggregate rate is way below the channel capacity, the collision will be low. Because when does the collision happen? The collision happen if we have multiple users are trying to access the channel more often. So the more often the users will try to access the channel, the higher the probability that they will talk at the same time, which means the higher probability of collision. So what we will try to do is to reduce the aggregate rate of all the users. So we can restrict the number of users who are accessing the channel at the same time, which is what we have discussed before as over-provisioning. So we from the network point of view, we say, for example, we know that the theoretical channel bandwidth or the theoretical channel capacity is like 10 megabits per second. So we will allow at maximum 2-3 users who have average data rate of 3 or average data rate of even 2.5 megabits per second, which can get us, in worst case, can get us an aggregate of around 8 megabits per second. Since we have 10, we'll be fine because we have to have some overhead between the channel capacity and the actual throughput. So we will have to reduce the aggregate rate on the channel, on the average, to below 8 or even 7 megabits per second, which means the over-provisioning. That the channel capacity is much more than or significantly more than what the aggregate number of users want. Because if we leave it uncontrolled, what will happen is that once the aggregate rate reaches very close to the channel capacity, what will happen? The probability of collision will be very high. The probability of collision will be very high in that case. And in that case, we cannot guarantee any quality of service. So in an uncontrolled environment with no control on when to have access to the channel, the most common way is over-provisioning. Okay? Right. We're saying over-provisioning, but if we have number of users, the over-provisioning will fix the fact that we will reduce the collision. Right. We reduced the collision, but we did not provide service differentiation amongst the users. مفهوم? Yeah, we have 4 users are accessing this channel. We do over-provisioning. We say, okay, we have 4 users, each one of them is 2 megabits per second on the average. So the aggregate is around 8, and the capacity is 10, so I think we're fine. The probability of collision will be low in that case. It's not going to be 0, but it will be very low, which is what we called here over-provisioning. But those 4 users, if they use a protocol like cmpe482-2017-03-7, do you remember cmpe482-2017-03-7? Vaguely, huh? With collision detection. This is part of which standard? Which standard? The wireless or the? Huh? دي مصيبة. This is Ethernet. Wireless uses what? CA. Wireless uses cmpe482-CA. So instead of D, you use A. Because again, in wireless, we can never detect collision. And we talked about why from 455, huh? We talked about how we cannot detect collision in wireless. We cannot, we just cannot. So instead of detecting the collision and doing something about it, we can try to avoid, but we cannot detect it. So in wireless, we use cmpe482-CA. In both cases, what we are trying to do is, if there is collision, then we do a back off. You seriously need to go and refresh it. So if there is collision, nodes will back off. Okay? When they back off, معناها they go back and say, okay, I will wait for a certain period of time, and then I will try again. Okay, so that's what back off means. This back off time is calculated based on based on uniform distribution. They wait for a random period of time. Okay, why random? This random will guarantee 2 things: that hopefully when they generate a random number, they will generate a different random number, which means that the next time they will try, they will not collide. They will not, because if I say wait for 10 milliseconds and then try again, somehow I will wait for 10 milliseconds, they will try again, there will be a collision. Okay, it's not smart. So what we're trying to do is that the back off follows what we call a uniform distribution number. So if they generate a random number between, let's say, like 0 and 100 milliseconds, so hopefully one will generate a random number of 10 and the other one will generate a random number of 30. So in which case, the one with a random number 10 will gain access first, and the other one will, when it comes the turn that it will access the channel, it will use a SISMA. It will do carrier sensing. It will realize that someone is accessing the channel, so I should stop. So this will solve, hopefully will solve the issue of collision in the next round. The randomness also guarantees fairness. So because when they generate a random number using a uniform distribution, the probability that any of them will gain access to the channel first is equal. Which means that over a very long period of time, they will have fair access to the channel. Because if one generates 10 milliseconds in one point and the other one generates 20 milliseconds, what will happen after some time is that the one who generated 10 will generate after that 20. And the one who generated 20 will generate 10. They will be different, but again, they will have fair number of trials to the channel. So the randomness guarantees differences, different times, and fairness. Okay? Why am I saying this? Because the randomness and fairness, احنا وظيفتنا ان احنا not to provide fairness. In this course, احنا what we're trying to do is not to be fair. To be equal, but not to be fair. Because fairness is against quality of service. Like complete fairness is against quality of service. Right? So we need to provide some way for service differentiation. How do we do this? We give some priority. So when they back off, they will not back off using the same random number that they generate. No. One user may select a specific random number in the order of tens of milliseconds, and the other one will generate in the order of maybe tens of milliseconds or 100 milliseconds. What I essentially did in that case is that I give more priority to people with low delays to access the channel more than the highest delays, the higher delays. So in that case, we're adding a priority scheme. So adding priority scheme comes based on the fact that we give the opportunity to some users to back off for a shorter period of time compared to other users. In that case, we are essentially giving more priority to these users over the other users. Okay? طبعا, I know that a good percentage of the students did not follow that. Let's try it on a timeline. So there are two nodes here at this point in time who had collision. They are trying to access the channel at the same time, so there is collision, right? So back off talks about the fact that these users, 1 and 2, they will generate a random number. This random number, hopefully here, it will be, let's say like 10 milliseconds, and hopefully the other one will be 20 milliseconds. So this one will wait 10 milliseconds, and the other one will wait 20 milliseconds. So the next time when this one tries to access the channel, it will gain access to the channel first, right? The other one, even if there is any overlap, there will be enough time for this node to realize through carrier sensing that it senses the channel, and it realizes that this one is accessing the channel, so it will abstain from accessing the channel, right? So this random number really guarantees that next time, hopefully, we will reduce the probability of collision. But again, if the load is high, sometimes collision happens repeatedly. And maybe every time with different node, because the load is really high. Like imagine if you are going through an intersection, if all the cars are coming through an intersection. This intersection is basically a shared channel, right? If you have traffic with high load coming from different ways, hopefully there will be no collision. But collision for us means that two cars will try to access the roundabout at the same time, so they will stop, and one of them has to wait. For us here, the wait time or the back off time is based on generating a random number. Okay? So this random number varies over time. So the one that generated 10, next time it will generate 20. If that's the case, then we have fairness, because one will go first this time, the other one will go first the next time. If we want to have priority, then we will give this one the priority to always wait for a shorter time compared to the other nodes, which means that if there is collision, this guy will have access next time to the channel before anyone else. مفهوم كده؟ أفضل؟
So the waiting time could be controlled, right?
Right. So the wait time we call it the back off time. So the back off time is controlled in the case of multimedia communication. Okay? It's still random, by the way. There's still some level of randomness here. But here, this guy will generate a random number in a window which is much larger than the high priority users. So the high priority users, they will generate a random number from 0 to 10, and the low priority users will generate a random number from مثلا 10 to 1000. Okay? So essentially, again, what we have done is that we have given more priority to certain users over the others. ففهمنا معناها ايه بقى ايه؟ Adding a priority scheme. So adding priority scheme by changing the back off time for different users or for different nodes. So in that case, the sharing of the medium is not fair. The sharing of the medium incorporates or integrates some service differentiation, and that's exactly what we want to do. Okay? This is for collision-based protocols. For collision-free channel access mechanisms, we have eliminated collision altogether. By doing what? By doing one of these two. Either time division multiple access is we divide the channel time simply into time slots, okay? And we predefine the order of these time slots to be assigned to certain users. So if I have 5 users, I would say this is user 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and so on. Okay? So by allocating a separate time slot to each user, I eliminate the collision, right? If we are in a meeting like this, and then we are going in order, so each one has to say something. If you don't want to say anything, then your slot will be wasted. But we have to wait until your slot is over, and then go to the next slot. Okay? Which one is more efficient, do you think? The collision-based or TDMA? This is a political answer. This is it's very close to being right. If the load is high, which means that the probability that everyone has something to say, right? In that case, TDMA will be good, right? Because for the other one, for collision-based, if the load is high, then the probability of collision will be high. And that's why we're trying now to get rid of all the roundabouts in Doha. Why? Because 10 years back, it was not populated as today, right? So roundabouts are really bad, really inefficient when the load is high. This is exactly similar. So if the load is high, the probability of collision will be high. So in that case, the throughput will not be good. But if for the controlled way, for the collision-free, if the load is high and everyone has his own slot, then the throughput will be almost 100%. But it's not as idealistic as we can see it now. There is some complication to it. So but in general, if some users, and this is actually more practical, we don't have the same requirements in terms of traffic, right? Someone is playing a video, another one is browsing the internet. So intrinsically, we don't have the same requirements in terms of traffic demands, right? So that's why the collision-free is not as sweet as we can think. Because if we assign these slots and predefine them before communication, chances are you will end up with some slots that are not utilized. And that's inefficiency. Although we have eliminated collision, but we have introduced another overhead, which is a number of slots that are not utilized. So what they do here is that they assign these slots dynamically. So the number of the slot assignment is not prefixed. The slot assignment is based on the demand of each user. So we can say this number of users, they have these traffic demands. So it looks like you are running a video, so you need more bandwidth. More bandwidth to me is like 2 slots in one frame. So in this frame, I will assign 2 slots here, 1 slot here, 3 slots here, and so on. Okay, so this is service differentiation. So we have differentiated amongst the users. So the prefixed time slot is not always efficient, and actually in most of the cases not efficient. So the best way is to do it dynamically. And even with dynamic, it's not the same every time. So maybe the same user who had 2 slots in this frame will have 1 slot in this frame and will have 3 slots in this frame. This is bandwidth management. Bandwidth management is to say, we will dynamically assign the slots based on the requirements of the applications that the user are using. Okay, so this is a whole new set of algorithms that this is an area of research, and people can work here like for 5 years to do PhD for just bandwidth management. Okay, but for us, the prefixed TDMA is generally not efficient, so we can assign these slots dynamically or unequally, and in that case, we are introducing service differentiation. Okay, so service differentiation is introduced for collision-based by waiting different time, in which case we give more priority to certain users. Here, we're giving more slots to certain users as a favor, which means that we are, again, giving high priority to these users. Pooling. Pooling tries to overcome the problem of assigning a time slot to someone who doesn't want to say anything. Okay? So in that case, pooling is centralized. So we have a moderator for the meeting. Okay? The moderator will go in turns كده in order. Do you want to say something? Do you want to say something? Do you want to say something? If you don't want to say anything, then he switched to the other one. Which means that he's giving a slot only for people who want to say something. What is the cost here? لا. The cost here is the centralized organizer. Because for TDMA, we don't need anyone to organize, right? We predefine the slot assignment, and then we start working. We don't need anyone to organize anything because it's pre-organized for us. But pre-organizing this may run into the risk that you assign a time slot to someone and he doesn't want to say anything. And in that case, the slot is wasted. Pooling tries to overcome this by having a centralized controller. So I will have to go in turn. If you don't want to say anything, then I will switch to the next one. Okay? So pooling requires centralized controller. Which is, in our case, pooling is done on Wi-Fi, by the way. And what is the main controller, you think? Loy. What is the main? Who controls the pooling in the case of Wi-Fi? Who controls the turns? Who controls the pooling in the case of Wi-Fi? ده سهل ده ملوش علاقة بالنصيب. ليه؟ لا in Wi-Fi احنا we have مش راوتر اللي هو الاكسس بوينت. اللي هو الاكسس بوينت. So channel access for Wi-Fi is done using the access point, which in our homes we have the access point is the router, it's integrated. But in normal cases, the access point works in layer 2 and router is layer 3. So in any case, the centralized controller in that case, because when you say router, you mean network control, network layer. Network layer doesn't have access to channel access mechanisms. This is layer 2. In our case, this is the access point. So we have a centralized access point, and it acts as the pooling controller or the coordinator that goes in turns. Do you want to say anything? If the answer is yes, then I give you the slot to send. If you don't want to say anything, then I switch. So how can we provide service differentiation in that case? Because if I go in turns, this is fair, right? If I go in turn, this is fair. How can we control the service differentiation in that case?
Don't go in turn. Don't go in turn.
Don't go in order. بالضبط. برافو عليك. So if we switch the order every time to give more chances for certain people to send, this is essentially service differentiation. What else? I can give turn with longer duration to certain people. I control everything. I'm the main controller. I can do whatever I want. So either I can change the order every time and I ask you more often, or when I ask you and you want to send something, I'll give you more duration. and I keep everybody else, idle until you finish everything. So in pulling, we can provide some service differentiation by changing the order of pulling every time. ده فهمنا كده؟ يبقى for TDMA, I give more slots to certain users with more priority. In pulling, I give them with different order, give them more chance to send. And for collision-based techniques, I give them different back-off delay. Different back-off delay. ماشي? So this is for channel access. So يبقى احنا كده اتكلمنا عن classification. So we talked about classification in different layers, and we talked about channel access mechanisms. The next one is what we call a packet scheduling. And packet scheduling, as we said before, we have one or more queue inside the node, and then we want to, it's similar to polling, but this is inside the node. Here, the scheduler, what it does is that it can take one packet from here, one packet from here, and one packet from here, and so on. So it's a scheduler. The packet scheduling has two levels. We have what we call intra-station packet scheduling. Intra, when I say the term intra, what do I mean? Locally, بالضبط. يعني inside the station. Intra-station معناها inside the station. Which means this. Okay? So this scheduler is what we call intra-station packet scheduling. So I actually schedule the packets inside the same node. And there is another level of packet scheduling, which is very similar to channel access mechanisms, which is what we call a inter-station packet scheduling. Inter-station is that I schedule the traffic coming from multiple stations, which is essentially channel access mechanism. Okay, so we have a network, and then I organize the packets that come from different users to go to the network at certain point in time, which is quite similar to channel access mechanisms, right? So here I can use packet scheduling in the case of collision-based or in the case of collision-free, using time slots, using pulling, and stuff like that. So mainly what we need to talk about is the intra-station packet scheduling. So what I want to do now is to go through this packet scheduler and design a specific queuing scheme. Okay? Similar to the fact that we're entering into the bank. So whether we go all in the same queue, which means that we essentially have the same type of service. Okay? And when we go through the same queue, it's first in, first out. And in that case, it's completely fair. Okay? Or I can still provide complete fairness through multiple queues. But in that case, I take one from here, one from here, one from here, one from here. Okay? So in that case, also I can have multiple queues, but complete fairness. So we want to, again, introduce service differentiation in the case of packet scheduling. So we can provide, hierarchical here means that we can provide the packet scheduling on two levels. There is one level who are intra-station, and there is inter-station. By providing different queuing scheme or different scheduling schemes in a hierarchical way, we can introduce the service differentiation, and we can provide different behaviors to the different users. Okay? So the simplest type of queuing or packet scheduling is what we call 5. We all know 5, right? So first in, first out. So all the applications will go into the router. Okay? And the router has only one queue. It's like we are all entering the same bank. We all line up in the same queue. So first one, first in, first out. Very simple. Okay? So here, this is completely fair, and always complete fairness comes with the fact that it's best effort. It's best effort معناها ايه؟ It's the opposite of service differentiation. So we're not guaranteeing anything. We cannot guarantee any quality of service. We cannot guarantee any quality of service, neither on the packet loss, nor on the packet delay, nothing. We cannot guarantee what jitter will look like. We can never guarantee anything. It's best effort. Even if some packets get dropped, I cannot do anything. It's best effort. So no service differentiation in that case. So the only way for us to provide, this is a very important section here. We can use best effort with no special packet scheduling, but we can provide certain level of quality of service in that case. How? The problem here is that if some of these applications are misbehaving, like imagine if this one is video, and this one is text, and this one is audio. What will happen? We're all entering the same queue, right? So this video will enter in the queue more often, right? So it will eat the whole bandwidth and the whole queue from all other applications. Okay? Someone might say, "Tama video, we need more quality of service for video, and it's taking." But imagine if I have anything other than video, because video we need more, maybe more bandwidth. So it's not a good example here. But imagine if we are sending any information with a huge amount, and this application is taking the whole queue. What will happen? Other applications will starve. This queue will not really do anything special, will allow all the traffic coming from different users, FIFO and everything. So it's best effort. Sorry, I cannot provide any guarantees and things like that. If we want to provide some quality of service, then we can introduce the concept of traffic policing. Remember, we talked about the fourth mechanism. We can introduce some quality of service in that context by introducing traffic policing here. Is to say, the application that is misbehaving is trying to send many packets in a short period of time. No, I will restrict it. So I will sort of constrain the traffic that is coming through the queue before it goes into the queue, because once it goes into the queue, I have no control. They will go in order, they will go in turn, they will take fair access, and that's it. I don't have any control. In that case, the only way to introduce some kind of quality of service is by doing traffic policing. Okay, we'll talk about traffic policing and traffic shaping in a later stage. So we'll talk about these mechanisms. Or admission control, or to say, based on this user ID, I will stop this traffic altogether. I will not allow it to go into the queue at this point in time. So the only way for me is just to stop or to police the traffic before it comes into the queue. Because once it goes into the queue, I have no control. Imagine? But this is the simplest way. Okay? We'll stop here.